In computer vision and image processing, convolution is a way to mathematically filter images to do things like blur, sharpen, or edge detection. I'll show you examples of those later, but first let's see how convolution is performed. Convolution is the process of adding each element or pixel in an image to its neighbors, weighted by a kernel. A kernel is a small matrix that does not change throughout the convolution operation and holds the weights for this summation process. I usually see kernels as 3x3 or 5x5 matrices, although other sizes do exist. The numbers in the kernel determine the type of filtering that we do. I'll pick these for this example. Next, we take a section of pixels the same size as the kernel, starting with the top left of the image. Each pixel is multiplied with the corresponding kernel element. All the values in this element-wise multiplication are then added up to give us the first value in our output image, or feature map. The window then slides over by one pixel and the operation is performed again. We use the same kernel but a different subsection of the image this time. This gives us our second value. The window slides again to give us the third value. When it reaches the end of the row, the window slides down one pixel and starts again on a new row. This process continues until we have used all of the pixels in the original image to create a new output image. All of this assumes a stride of 1, which means the window moves over or down only one pixel at a time. With a stride of 2, we would start by computing the weighted sum of the window set in the upper left just like we did before. Then we would slide the window over by 2 pixels and repeat the calculation. We would move the window down by 2 pixels as well to repeat, but since we cannot do that, the convolution is done, and we end up with a 2x1 array for the output image instead. You'll also notice that the output image in any of these cases is smaller than the input image. There are a few ways we can account for this, which I'll talk about in a minute. But first, here is the general formula for image convolution. Capital I is the input image matrix and capital K is the kernel. We index into each of these arrays and sum the element-wise multiplication to get a value for one of the pixels of the output image O. Often in the math world, you'll see that matrices and vectors start with 1 for the first element. However, I've shown the equation for starting with 0 as the first index, as this should be easier to implement in code. S is the stride. H, which I'll show in a second, is the height of the image, and W is the width. Capital M is the number of rows in the kernel, and capital N is the number of columns. Lowercase I is the row index of the output image, and it goes from 0 to the floor of the image height minus the kernel height divided by the stride plus 1. Lowercase j is the column index of the output image, and it counts from 0 to the floor of the image width minus the kernel width divided by the stride plus 1. Here is an example of our previous convolution example with the zero-based indices marked for each matrix. The output image would be a 2x3 matrix if we set the stride to 1. Let's say that we're working with a really odd kernel like this, which causes the output value to be really large. If we're working with 8-bit grayscale values for our input image, then we would usually want to work with 8-bit grayscale values for the output image. These values must be between 0 and 255, so we usually set anything above 255 to 255 and anything below 0 to 0. You'll sometimes hear this referred to as clamping a value. In this case, we'd be clamping the value between 0 and 255. If you're curious, the output image would look something like this, as all values would just be clipped to 255. If you're working with floating point values for your pixels, which can sometimes happen in machine learning, you'll also want to clip or clamp those. 0 to 1 is the normal range, but you might sometimes see -1 to 1 as well. Now, let's talk about padding. Vincent Dumoulin made these great animations and shared them on GitHub. I'll use them to demonstrate how padding works. There are a few types of padding that you can use on the input matrix. We've been looking at what's known as valid padding, which essentially means there's no padding of the input image. Only the valid elements of the input array are used. In this instance, the input image is a 4x4 matrix and the kernel is 3x3. The kernel isn't shown, but we can assume that the element-wise multiplication and summation are occurring to give us the element in the output array shown at the top. With a stride of 1, the output array is a 2 by 2 matrix. We saw this example earlier, where we convolve a 4 by 5 input matrix with a 3 by 3 kernel and use a stride of 2. Notice that while the top 3 rows are used, the bottom row is skipped because we would not be able to move our window down by 2. We only use the elements in the input matrix that are valid with the given window size and stride setting. In same padding, we pad the input matrix with elements in order to give us an output matrix that is the same size as the input. The padded elements are shown by the dotted lines. For example, here we show a 5 by 5 input matrix with a 3 by 3 kernel and a stride of 1. With these elements added around the input matrix, the output matrix will be 5 by 5. Note that even with padding, if you set the stride to more than 1, you still may end up with an output matrix that is smaller than the input matrix. In some libraries, like Keras, if you specify same padding, it will attempt to add as many padded rows and columns as necessary to give you an output matrix that is the same size as the input matrix. There are a few ways to fill the padded elements. One common approach is to just set all of the padded elements to 0. This technique is probably the most common, and it's what Keras does when you specify same padding. Another option is to copy the values on the edges of the matrix out to the padding. This has the effect of making the image look a little bigger than it is and preventing some skewing of the data at the borders that might occur if we use 0 padding. In some applications, you don't need to maintain the information at the borders, so you can get away with no padding. In fact, it's more computationally efficient to work without padding. Not only does it save you convolution steps, it also gives you a smaller output matrix, which might be beneficial for future steps. For example, if you're using this filtered output image as an input to a neural network, having a smaller matrix means fewer input dimensions and therefore fewer computations in each node. However, there are times when you want to use padding. For example, if you're just looking to filter an image to blur or sharpen it, then you will likely want to maintain the same size and shape. Keeping the same shape also means you can perform more convolution steps without continually losing information at the borders. And sometimes you might determine that the information at the edges of the image really is important to whatever vision project you're doing, so you need to use padding to keep that relevant data. If you're working with color images, you would first break the image apart into its separate red, green, and blue color channels. Each channel would then act like the grayscale images we were looking at earlier. A separate kernel would be convolved with each channel to produce 3 separate output images. These output images represent the new RGB channels and could be combined to create the new filtered color image. Note that the kernel can be the same for each channel, but it doesn't have to be. You could use different kernel values for each channel if you wanted to. This would create some interesting effects, as you might blur one color, sharpen another, and do edge detection on the third. When working with color images, you no longer have a simple two-dimensional kernel. Since you have one kernel for each channel, you can stack the kernels together to create a three-dimensional array. In this example, the first 3 by 3 matrix would be for the red channel, the second 3 by 3 matrix would be for green, and the third 3 by 3 matrix would be for blue. When working with something like NumPy, SciPy, or Keras, it's often easy to store these kernels together, so you would likely store them as a single 3 by 3 by 3 array. Using convolution, we can create a variety of filters for our image. Let's look at a few filters that have been applied to this elephant photo. Note that I'm using a small image, 200 by 130 pixels, so that our 3 by 3 kernels will have a noticeable effect. First up is the Gaussian blur. This simply mixes the pixels in the window in such a way to soften transitions and edges. We can also use the kernel we saw earlier to create a sharpened image. Note that sharpening an image using this method will also amplify any noise present in the image. We can also do this funky emboss effect to make it look like the elephant is carved out of the page. In addition to forming the basis for fun effects for things like Instagram filters, we can use convolution to do edge detection. The first is a basic outline that picks out any areas of harsh transition between light and dark. The next is a Sobel filter, which is a combination of two filters that pick out edges in the X direction and Y direction. Edge detection is extremely useful in computer vision as it helps us determine the boundaries between objects in the image and the background. It can also help reduce noise. This is the kind of information that a machine learning model can use to pick out objects in an image or extract features like patterns and shapes to use for classification. We can set the kernel parameters manually if we know what kind of filter or filters we want to use. Alternatively, we can use learning algorithms to set them automatically during the training process if we are using something like a convolutional neural network. In this case, the algorithm essentially tries a bunch of different filters and picks the ones that give it the best features to meet its goal, like classification or object detection. I hope this helps you get a sense of how image convolution works, how we can use it to create fun filtering effects, and how it forms the basis for feature extraction for many computer vision applications. In addition to convolution, we can use other operations like pooling to downsample the image. This has the effect of reducing the size of the data, as well as creating a consistent feature map that stays the same regardless of small variations in position of the subject. There are a few popular techniques for pooling. The first is average pooling. To perform average pooling, a window is applied over the top left section of pixels on the input image. You'll often find windows in 2x2 or 3x3, but they can be any shape. The pixel values under that window are averaged to produce a single output value, which is stored in the output image. The window slides over to the next set of pixels. In most cases, the horizontal stride is the same as the window width, and the vertical stride is the same as the window height. You'll usually want to avoid overlapping the window in pooling, as the idea is to downsample the image. Notice that I'm skipping the last column, as I'm unable to fit a window without overlap. This assumes a valid padding scheme, which we talked about in the convolution lecture. With valid padding, we do not add any padding to the input image. You could also perform same padding. This would add additional rows and columns of zeros or other values so that you're not losing information on the edges. Also, notice that I'm rounding the output values when storing them to my output array. For pooling with arbitrary data, you would likely not need to round or truncate the data. However, since I want my output to act like an image, I need the values to be 8-bit integers, so I round the values and make sure they're between 0 and 255. Another popular form of pooling you'll see is max pooling. It works similarly to average pooling in that we use a sliding window to compress the features in an image. This time, instead of computing the mean of each group of pixels, we simply pick the element with the highest value and keep that. We slide the window to the next group of pixels and repeat the process. We keep doing this until we have found the maximum values for all of the window positions. There's less math involved in max pooling, which potentially makes it more efficient. It also allows us to pick out the most salient or important features in an image. You could also have min pooling, where the minimum value is kept, but max pooling is much more popular. Something else that you might come across is global pooling. This is where the window is the size of the entire image. You can have global average pooling, where the average of all the pixel values is calculated. Once again, I'm rounding to store the output as an 8-bit integer. You could also do global max pooling, where only the maximum pixel value of the whole image is kept. Global pooling is used to aggressively downsample an image or to simply denote the existence of a feature. When it comes to convolutional neural networks, you'll often find pooling operations done after convolution, which means that pooling is done on a filtered image that does something like edge detection. Pooling allows us to compress the image in a way that keeps those highlighted features from the convolution step. Let's take a look at a filtered image of the same elephant we saw in the convolution lecture. Here, we did a simple outline or edge detection filter. If we perform a max pooling operation on this image using a 2x2 window, we get something that looks like this. First, notice that the output image is much smaller as we've reduced the number of pixels by 1/4. If we then decide to feed this filtered and pooled image to a neural network, that's a lot fewer dimensions and parameters to work with. Average pooling makes the image look like it's simply been downsampled. Some of the edges might get lost, especially, it seems, on diagonal or curved lines. Now, let's compare this to the max pooling operation. As you can see, the edges are much more pronounced. This is because edges are higher valued numbers in the matrix, much closer to 255 than, say, 0. As a result, the max pooling operation keeps those in the output image rather than trying to average them. When it comes to picking out features after a filter like an edge detector, the max pooling operation does a better job of highlighting those sharp features than average pooling. However, max pooling can lose some of the finer details, as it simply drops the non-highest values in each window. If those details or smooth transitions between areas in the image are important to your application or model, then you may need to use average pooling. That being said, I see max pooling used much more often with convolutional neural networks for image classification. Another important feature of pooling is that it provides some translation invariance for feature sets. This means that different images can have the main subject in slightly different locations, and the output feature set generated by convolution and pooling can produce the same or similar feature maps. For example, let's say that we're looking at a zoomed-in portion of an edge that's on the elephant we saw earlier. A max pooling operation would produce an output like this. Now, let's say we have another image of an elephant, but the edge is shifted by a few pixels. The max pooling operation would give us something like this. Not exactly the same as before, but it's similar. Both outputs let us know that there is an edge in that general area. This helps generalize the location of features in similar images. When it comes to machine learning, it can help train a more robust model that looks for features in general areas rather than have the model look for exact pixel values in certain locations. I hope this demonstrates how convolution and pooling can work together to extract features from images. This combination forms the basis for the first half of a convolutional neural network. All of the basic building blocks that make up a simple convolutional neural network, or CNN for short. Let's see how those pieces fit together to create a robust image classifier. Here is a very simple example of a convolutional neural network, and one that you might see doing basic image classification in an embedded system. We'll assume that our input is a grayscale image. Remember that a grayscale image is just a two-dimensional array of numbers. These numbers might be floats normalized between 0 and 1. They could also be unsigned 8-bit integers between 0 and 255. In some fully optimized models, which we'll see from Edge Impulse, the model might expect a quantized input where the input values are normalized and cast to a signed 8-bit integer value. In this case, the values will be from -128 to +127. The library we download from Edge Impulse should handle this quantization and normalization process for us, but it's a good idea to pay attention to what the model is looking for as an input. Note that the input should always be the same shape. If you trained a model to accept 28 by 28 grayscale images, you should always feed it 28 by 28 grayscale images. Next is one or more convolution layers, where each is followed by a max pooling layer. Note that a layer shown here is not a single convolution or pooling operation. Each layer may contain dozens or hundreds of simultaneous convolution or pooling operations to generate a number of feature maps that are passed onto the next layer. Using multiple stacked convolution and pooling layers like this allows the model to extract more complex features from the image before sending those features to the classifier. After going through convolution and pooling, the features are then stacked and flattened to create a one-dimensional vector. This vector is then fed to a dense neural network to perform the actual classification. The neural network can be more than one layer, but sometimes one layer is good enough, as I've shown in this diagram. The output goes through a softmax operation to give us our output predictions. This flattening and dense neural network step might look similar to the simple classifier we trained at the beginning. However, instead of feeding it raw pixel values, we're now giving it features that have been computed from the convolution and pooling layers. These features ideally include things like edges, blobs, patterns, and so on, which is closer to how we humans interpret images. Let's break down these layers. First, let's look at the convolution layer. Each layer will have some settings associated with it, and these settings can be treated as hyperparameters. This means you can adjust them before training, but they are not automatically updated during the training process. Two popular settings are the number of filters in the layer and the shape of the kernel. A 3x3 kernel is fairly common. Let's say we have 4 filters in this layer. Each filter has a stride of 1, and we would use same padding so that the output features are the same shape as the input image. Our image would be filtered in parallel 4 different times with 4 different kernels. Each of these kernels would extract a different set of features. For example, a few of the filters might perform edge detection, while another blurs the image to get an overall placement of the object. However, these kernel values are not set manually. They are randomized initially, and they are updated incrementally as part of the model training process. In effect, the model is learning which features it should look for to achieve the desired classification outcome. Another important difference between a convolution layer in a machine learning model and basic convolution is that the convolution layer also has a bias term. This is a simple constant value that is added to every element in the output array. The constant is the same within a filter, but each filter can have a different constant value for the bias term. Like the kernel values, the bias term is also a parameter that gets updated during model training. These output images are very contrived for this example, as they're using manually set kernel values to create a particular filtered output. So, while we might think that the model is looking for edges or blobs or shapes, in reality the features end up looking something like this. The kernel values are learned and can often look random and weird. Sometimes it can be difficult to figure out exactly what features a particular filter has been trained to pick out. These images were created by using kernel values from a real CNN that was trained to classify these electronic components. The filtered images are then sent through an activation function, just like you would find in a neural network node. Without activation, the filtered images are just created through a series of multiplication and addition steps. Activation adds nonlinearity into the process to assist with training and potentially help normalize the output to be between two values like 0 and 1. One popular activation function is the sigmoid function. This converts any number into a value between 0 and 1. In recent years, the rectified linear unit, or ReLU, has become more popular as it can make training faster and is often more computationally efficient than other activation functions like sigmoid. Each pixel value in the filtered image is sent to the activation function, and the result is the output of that convolution step in the layer. While we can depict these output arrays as images, it's usually more helpful to think of them as arrays of features rather than images. When working with floating point values for this convolution step, the values for the pixels and weights can be almost anything. As a result, the ReLU function will operate as intended. You just need to convert any value that's less than 0 to 0. If you try to imagine these feature maps as images, then you'll probably wonder how ReLU works on 8-bit pixels with values between 0 and positive 255. In a fully quantized network, weights and bias terms are often stored as signed 8-bit integers. In each layer, the input image or feature map gets quantized to 8-bit signed integers as well in order to make the filtering and activation functions faster on processors without special hardware floating point units. Rather than 0 to 255, the pixel values might be mapped to negative 128 to positive 127 and stored as 8-bit signed integers as well. This way, negative values are possible during the convolution step, and they can be sent through the activation function. For ReLU, any values less than 0 are converted to 0. For the purposes of visualizing this step, it simply means that any shade darker than 50% gray becomes 50% gray, assuming this is how the quantization process set the midpoint of our pixel values. The quantization process can get fairly complicated in TensorFlow Lite, as a different 0 point could be set for an activation function. This might help give more precision for activations of filtered images with more light colors, like the one on the far right. While the filtered images and activation feature maps look similar, if you look closely, you can see that any of the dark shades have been converted to a middle gray to demonstrate how this ReLU function might work. What's left is a collection of prominent features for that particular convolution filter and activation. Note that you may often see one of these filter and activation functions referred to as a neuron or node. This can help you think of the individual units in a convolution layer in terms of a neural network. I'll shorten each of these nodes to a circle, which contains the convolution filter, adding the bias terms to each value, and the ReLU activation step. This gives us a feature map as an output for each node. While we could send these feature maps to another convolution layer or write to a fully connected neural network for classification, you'll sometimes find a pooling step after convolution. Max pooling is one of the most popular pooling operations, and it's what we'll use in our examples. Here, the pooling operation is performed on each of the filtered images to produce a new output feature map that has been downsampled and has the most salient features picked out. Each of these new feature maps is now 14 by 14 pixels. Rather than thinking of them as a separate collection of feature maps, you can also stack them together to create a three-dimensional array of feature maps. This array would have the dimensions of 14 by 14 by 4. This collection of feature maps is used as the input to the next convolution layer. Here, we'll use 2 filters instead of 4, but the other hyperparameters stay the same. Each filter or node works the same way as before. The collection of images are convolved with a kernel, and a bias term is added to all pixel values to produce a new feature map. There's one big difference here between this layer and the first convolution layer. The input is now several images, or a three-dimensional array, depending on how you look at it. Instead of a single 3x3 kernel to filter the image, each node now has a collection of kernels equal to the number of input feature maps. Each of these 4 kernels has its own set of parameters that are determined during model training. So even though a single filter might say it has a single 3x3 kernel, it really has more than that depending on the number of input images. Let's see what's happening in the node on the left. Here, 4 separate kernels are being used to filter each of the input images. Rather than output 4 separate new images, the values under the windows, after being multiplied by the weights in the kernel, are being summed together, plus a bias term to give us a single new value in the new image, or feature map in this case. In other words, this is how groups of pixels are being filtered and combined across several images to give us a new pixel value in the output image. The same thing happens in the other filter. Next, a nonlinear function, like ReLU, is applied to these arrays to give us the outputs of this layer. Each of these feature maps is a combination of the feature maps that were supplied to this layer. After that, we perform another max pooling operation on each of the 2 feature maps. This gives us downsampled features that are each 7 by 7, assuming we use a pooling window of 2 by 2 with a stride of 2. These are distilled features of the original image. Ideally, as the network trains, it settles on weights in the various kernels that help pick out the best set of features. The final step in this section of the network is to flatten the feature maps. Here, each pixel or array value is stacked end to end to create one long vector. When the end of one feature map is reached, it simply moves on to the next. Instead of a 7 by 7 by 2 feature map, we now have a 1 by 98 vector of features. This is very much like how we flattened our image when we tried the dense neural network for classification. The difference is that instead of using the raw pixel values as input, we're using these features, which should represent salient points in the input image that a neural network will care about. Part of the appeal in using convolution is that the input image can ideally be compressed into a set of important features. If you were to use the raw flattened image, you would have 784 values going into the next section as opposed to 98. You have to do some computation in this convolution section, but it potentially saves you some calculations down the road. This is especially true if you're working with large images. A 200 by 200 pixel image would be 40,000 input values, and doing some convolution and pooling steps could potentially reduce that down to a few hundred. Convolution layers allow you to condense an image to important features, possibly by using a lot of convolution and pooling layers to create a deep network. These layers take into account the relative position and neighbors of each pixel value, rather than just assume that the raw values are the features. At this point, the features are then fed to a dense neural network, which we covered in a previous lecture. It works the exact same way. One or more layers of fully connected nodes sum weighted values of their inputs and apply a nonlinear activation function to the output. This classifier section can be as deep or shallow as you'd like. In simple, tiny machine learning applications, you may only need one layer as shown here. My electronic components images would probably have 5 classes, but I've shown 3 here as an example. The output layer of your dense neural network would likely pass through a softmax operation in order to give you the output probability of each class. I've listed the dimensions at the input and flatten stage to give you an idea of how the feature extraction section can reduce the dimensions. Note that this assumes 4 filters in the first convolution layer and 2 filters in the second convolution layer. If you use more filters in the last layer, there will obviously be more features at the flatten operation going into the classifier section. I encourage you to play with the architecture and various hyperparameters like the size and number of filters, number of layers, depth of classifier network, and so on. I hope this helps give you an understanding of what's going on inside a convolutional neural network. You may or may not see an improved accuracy over just a dense neural network, but the convolutional layers can help reduce the total number of operations inside the network, which makes the model more efficient. Now that you've seen the inner workings of a convolutional neural network, let's see how we can use Edge Impulse to train one. For this demonstration, I'm going to be using the bitmap images that I collected from my OpenMV camera. If you'll notice, go into your dataset and pay attention to the format of the images. Mine were all taken in BMP or bitmap format. Edge Impulse requires PNG or JPEG images, at least at the time that I recorded this. In the future, that may change, but since I have BMP only from my OpenMV cam, I need to convert these to PNG or JPEG. I'm going to go with PNG because it's a lossless format. You can convert them individually manually, but that takes up a bunch of time, or you can find some program. On Windows, there's this program called Bulk Image Converter. I'm going to use that. So I'm going to go where I stored my data set, which is in Python, datasets, electronic components, BMP, select that. I'm going to include the subdirectories. I'm going to convert BMP to PNG. I'm not going to delete them, and I'm going to click Start. That should be pretty quick as the files are pretty small. You'll notice what happens is if you go into the folder, it puts it in the same folder. So all the PNG files are now in here. Next, I'm going to go to Edge Impulse. I'm going to log into my account, and I'm going to create a new project. I'm going to call this one Electronic Components-CNN. When it's done, it should drop me into the dashboard. I'll click out of this pop-up, and I'm going to go to Data Acquisition. I'm going to click Upload Data since I already have it stored on my computer. I'm going to choose Files. By the way, you can see the supported files here. You can do what we did earlier in Colab and convert it to raw CBOR, JSON, or CSV format, where it's just the raw pixel values, whether that's 0 to 1 in floating format or 0 to 255 in grayscale, or even color if you don't mind having some extra dimensions in there. WAV is for sound files. PNG or JPEG is for our image files. That's what's supported at this time. I'm going to go to my data set, which I keep in Python right now. I'm going to go into the BMP folder, and I'm going to go into my first class, which is background. I'm going to select all of them, which should be all of the PNG images. Click Open. I'm going to automatically have it split between testing and training sets, and I'm going to enter a label. You can name the files with something like background dot and then the number of the file, and then that will allow it to infer the class. As you can see here, anything before the dot to determine that label. But since I don't have the files named like that, I'm going to enter the label manually. I'm going to repeat this process for each of my classes. So here are the capacitors. Change the name, or change the class name. And then we're going to do this again for the diode. Once more for the LED. And you'll notice that the images are color images right now. I don't mind storing them as color images in Edge Impulse. We're going to use Edge Impulse to convert them to grayscale before training our model. And then the last one is the resistor. When that's done, I can click Data Acquisition again, and I can see all of the different images that have been stored in my Edge Impulse project. And I should see the 5 different labels: LED, resistor, background capacitor, and diode. If I go to test data, you should see where some of the data set was split apart. About 20% should appear in test data. That may not always be exactly the case, but this is a good mixture here. This is a fairly small data set. I highly recommend getting more samples than what I have here. But this is a good place to start just to see if we can train something. I don't expect it to be very accurate, kind of like what we saw with the dense neural network. From there, I go to Impulse Design. It's going to ask me to input the image width and height because it's going to resize the image. So for these, I want to resize them to 28 by 28. And then you can pick how the resizing is done, where it scales versus where it crops. You can squash it, you can fit. I'm just going to leave it fit because it should keep the 1-to-1 ratio when it scales from the square 96 by 96 to the 28 by 28. I'm going to add a processing block. That's going to be an image. It's going to do some very, very basic processing. And then I'm going to add a learning block. It recommends doing transfer learning, but we're not going to do that. We're going to come back to transfer learning in a later lecture because for right now, I want to show you how to use a basic neural network to accomplish this task. So for neural network, click Add, save your impulse, go to Image so that we can extract features from these images, or rather than extracting exactly features, we're going to convert them to grayscale and resize them. So rather than RGB color depth, click grayscale, and that's the only thing we have to work with right here. So save parameters, and then click generate features. This will then create our grayscale images that are now 28 by 28 each and store them in our project. That's what we're going to use to train our classifier. And remember, that's what our classifier, our model, when it's done being trained, will expect 28 by 28 pixel grayscale values as input. So keep that in mind when we go to deploy the model to our embedded device. When it's done, you should be able to look around the Feature Explorer. Keep in mind that this is not all of the dimensions. There's some special math going on the back end to kind of squish those 28 by 28 dimensions down to 3 dimensions so we get an idea of how different the images are. From this, there appears to be very good separation among the classes with the exception of diodes and resistors. These are mingled together a good bit because many of the resistors end up looking like diodes and vice versa. So I would expect the model is going to have a hard time distinguishing these unless we get more data in here and we could get better separation among the classes. But for now, this should be good enough to try a few things. Let's go to the neural network classifier. The number of training cycles, I find that for a basic two-dimensional convolutional neural network, 10 cycles is not enough. This is the number of epochs that are required to train the model. I usually go with something like 100. Learning rate is fine to leave at the default. The minimum confidence rating is something that Edge Impulse does when it's trying to test and evaluate the network, so we can leave that alone. And I'm going to go ahead and show the default network architecture. Note that you can add extra layers here. You can add more convolution and pooling layers. You can also adjust some of the hyperparameters. So I can click on this to adjust the number of filters. In the concept lecture, we showed this as having 4 filters and this as having 2 filters. And there was no dropout layer here. But a lot of these convolutional neural networks need a lot more filters than what I showed in that concept video. Because of that, we're going to leave the default of 32 filters for for the first layer and 16 filters for the next layer. You can also adjust the kernel size. Kernels can be rectangular. It could be a 4x6 array. However, Edge Impulse only supports square kernels, so 3 means a 3x3 kernel for each filter. And then there's also the number of convolutional layers. You could stack convolutional layers prior to a pooling layer. And it comes with a pooling layer, which I believe is a max pooling layer. We can check that in just a second. After those 4 layers, which is convolutional pooling, there's a flatten. There's also a dropout layer, which helps with overfitting. This is where some of the connections are dropped or disconnected prior to going to the dense neural network, and this only happens during training. This has the effect of helping with overfitting, so I'm going to leave this in, but you can feel free to play with this rate. This is the percentage of connections that are dropped going to this dense neural network. There is only one layer in this dense neural network, and that is a 5-node neural network, 1 node for each of the features, and that's going to be our actual classifier. Everything up until that is our feature extraction that is trained automatically. If we go into Keras Expert mode, you can see exactly what's going on with the different layers. I was correct, it is a max pooling layer, as you can see here, and this is how you would use Keras to construct your neural network if you wanted to do this in Python. You would add a 2-dimensional convolutional layer, the number of filters, the kernel size, and the activation. You can see that they are using ReLU just like we showed, and the padding is same as opposed to valid, which means that the output array size and shape from this convolutional step should be the same as the input. After that, there's a max pooling, another 2-dimensional convolutional layer with 16 filters this time, one more max pooling, then a flatten layer, a dropout layer, and then a dense layer which has a number of nodes equal to the number of classes, which should be 5, followed by the softmax operation, which gives us the probability of each class as the output. There are some hyperparameters here if you wanted to play with those. This is the Atom Optimizer, which is a specific algorithm used to update the parameters in the model based on the difference between the expected outcome of each individual sample being fed through and its actual ground truth labels. We can control the batch size, which is the number of samples being fed to the model at a time prior to updating the parameters. And this is where the training and validation data sets are being set up so that they can be used for training and testing down in this .fit function. Let's go back to our basic view. And from there, all we have to do is click Start Training. I like to watch the training output in this window over here. As it's going, what I'm looking for is accuracy, and that is accuracy of the model on the training set, and comparing that to the validation or val accuracy. Both of these numbers should be going up. You can also look at the loss, which should be going down, but I like watching the accuracy for now. As you can see, accuracy is about 90 or over 90%, and the validation accuracy hovers around 90%. Because there is a difference between the accuracy and the validation accuracy, I can assume that there is some overfitting going on where the model is better at predicting samples in the training set than it is at predicting samples in the validation set. There are a number of ways you can address overfitting. Some of that might be playing with your network hyperparameters, which includes maybe adding layers or even removing layers, changing the number of filters, changing the number of neurons, putting in dropout layers, adding densely connected layers. You can try different architectures and configurations to see if you can reduce some of that overfitting. As you can see, our accuracy on the training set came out to be about 95%, but the accuracy on the validation set was a good bit lower. The other big thing that we can do is get more data. As I mentioned earlier, there's only 50 samples per class in this, and we should really be looking at having more than that. A few hundred samples per class at least to give us a better idea of what's going on and hopefully reduce overfitting in our model. When we looked at the Feature Explorer earlier, I noted that diodes and resistors looked very similar, and they both are actually kind of similar if you think about it from an object perspective. They're both cylindrical bodies with two leads or a lead coming out of each end, and I could see how a machine might confuse them, which means we have to figure out ways to train the machine better to look at the difference between those. And some of that might be better features where maybe we're using smaller kernel sizes to get those. These are just things to play with, but I did determine that we can use a convolutional neural network to mostly correctly identify the differences between or among these electronic components. We saw this a little bit in the concept video where I talked about quantization, where the actual weights and input features were quantized to 8-bit or 32-bit values, and then it was using integer math to compute everything inside of the network, which means you don't have to rely on floating point emulation or floating point units, which is specialized hardware in some microcontrollers and microprocessors. So that allows us to more efficiently run these networks on hardware like microcontrollers that may not have access to floating point units. This could save us some energy, this could save us some cost, a variety of reasons why you would want to do integer math instead of floating point math. But if you wanted to run the original network, you could click the float 32 unoptimized network or the unquantized version, and you can see it's about the same. So quantization doesn't lose us a whole lot of accuracy, so there's no reason not to go with the quantized version here, especially if we're going to run this on a microcontroller. Once you're happy with the results here, I'm going to call this good enough. For your purposes, I recommend playing with these. Try different numbers, try smaller kernel sizes, and see if you can get your accuracy up. I also recommend getting more data if you can, but I'm pretty happy with 90%. It's very similar to what we saw with the densely connected neural network. However, ideally, the convolutional neural network should have fewer parameters. It may have similar math or computational requirements, but it should have fewer parameters, which means it will take up less memory when we go to store this model. That may not always be the case. It depends on the number of nodes. It depends on the number of layers. There are a lot of factors that go into it, but ideally, convolutional neural networks should give us similar accuracy with fewer parameters and fewer steps to be performed. Once I'm happy with this, I can go to model testing. And I'm just going to click Classify All. This is my test set that was held out and never used for training or validation. I'm going to wait a moment while that tests all of them. And when I'm done, hopefully I get something similar to my validation set. Yes, about 90% accuracy. Once again, it's having trouble with both resistors, actual label is resistor, as well as falsely predicting other things as resistors. Now that we have a fully trained classifier, and hopefully you're happy with the accuracy and results of it, you can go to deployment and deploy it to your particular microcontroller or embedded system. There's a raw C++ library you could use, an Arduino library, as well as a MicroPython version for OpenMV, and even one for Linux. We'll be exploring these in a future lecture. One of the frustrating things about a convolutional neural network is that it can be difficult to figure out what's going on when the model classifies a given image. I'm going to show you a couple of techniques that you can use to get a sense of why a model made a particular decision. We'll start with our simple convolutional neural network that's been trained to recognize images of electronic components. For both of these methods, we need to remove the softmax layer at the very end. That's because the methods require the raw output values from the final layer of the dense neural network to compute the necessary heat maps. The first method is known as a saliency map. Here we compute the loss between the raw output of the network and the ground truth label values of a particular input image. The saliency map algorithm works its way backward through the network to figure out which pixels in the original image were the most important or salient in helping the model make the classification. These maps can look a little noisy, but it can be very instructive to see where the network was looking in the image. The second method is a class activation map. Here, we figure out which features from the final convolution layer were the most important in helping the network make its classification. Specifically, we'll use the grad-cam algorithm, which is short for Gradient Weighted Class Activation Map. Note that the resolution of the heat map will likely be different than that of the input image. That's because it's a feature map that results from one or more convolution or pooling steps. In fact, its resolution should match the output resolution of a single filter from the final convolution layer. In this case, we would expect a 14 by 14 pixel heat map from our particular model. I'm not going to go into the math behind either of these algorithms, as it includes a good amount of calculus to compute gradients. In fact, I don't even have a great understanding of how each of these algorithms work, but they can still be useful tools for debugging a convolutional neural network. What you can do is start looking at the saliency maps and CAM images for your test or validation sets. Here, I've created overlays for both maps that appear on top of the original image. This will help you get a sense of where the model is looking to make its classification. This resistor worked fairly well, although the spots in the corners of the saliency maps tell me that it's looking at the background sum to make a prediction. Next is a known good LED image whose label was predicted correctly. The saliency map shows that it was looking mostly at the corner and some of the edges of the LED. The CAM image is really interesting. The feature map around the edges seemed to be the most important. Finally, here's an example of a misclassified LED. As you can see, the leads of the component are cropped out of the shot. Both maps again show the model focusing on the edges of the component. However, the CAM heat map is closer to that of the resistor, where there are some curved edges near the center of the frame with a light bar at the bottom indicating some level of importance. What I also found interesting is that the model does not seem to care about the leads of either part at all. It focuses mostly on the component body to make its decision. Let's say you're trying to make a classifier that identifies dogs in an open field. Your training set looks like a collection of dogs on the left and a bunch of open fields like the ones on the right. Let's say you have a ton of training data and your model performs wonderfully on the validation and test sets. However, when you go to deploy the model, you find it performs terribly in the field. Why is that? In reality, your model is probably not detecting dogs, but rather it's looking for light backgrounds versus dark backgrounds. A saliency map or CAM can help you spot that. If the heat maps mostly focus on the background rather than your subject, you can determine that your model is looking for something else that differentiates your images rather than what you were intending. Let's take a look at how we can use our model from Edge Impulse to view saliency and class activation maps. We'll start with a trained model in Edge Impulse. From here, we'll need to download the trained model in order to use it in our demo code. So head to your dashboard, click out of the pop-up. You'll want the TensorFlow saved model file, as that includes a save point that we can load into Keras to use for classification and computing the gradients necessary for each of the maps. So let's download that file. It's going to be a .zip file. If you go into the GitHub repo for the course, there should be a section for the convolutional neural network visualizations. And if you go in there, there will be a Colab Jupyter notebook. If you click on Open in Colab, the page might freeze. So what I like to do is click on it and say Open Link in New Tab. This will bring you to Colab with the notebook. This will give you some information about the notebook, and let's run it one cell at a time. If you get the warning about the notebook not being authored by Google, click Run Anyway. After that first cell runs with our imports, we're going to want to point to our saved model.zip file. To do that, we'll want to click on the File Explorer, right-click in the area and click Upload. In Downloads, go to wherever you downloaded the .zip file, click it and say Open. Click OK, and that will appear in the Files area. You'll want to right-click on it and click Copy Path, and this is what you want to paste for your zip path. This will unzip the file, and if we refresh the File Explorer, you should see the saved model folder appear here. And this is a collection of files that make up your model, including a save point and some other files that are used by Keras to create your model. From here, we want to specify an input image. Go to your Edge Impulse project, and there are a couple of places that we can get image data from. First of all, if you click on the Image tab, you will see the screen. We don't want the raw features, as this is the information for the 96 by 96 color image. What we want is the processed features, as this has been scaled down to 28 by 28, which we specified in the impulse design, and converted to grayscale, as well as normalized to being between 0 and 1. This is what we want. So we can copy this to the clipboard, and we can go back into our Colab. I've got an example image here. I just want to delete this, paste in my features, and then I want to change the true index to whichever index match my labels here. Note that you're going to probably need to update these labels in order to match whatever labels you have for your project. Remember that Edge Impulse keeps these in alphabetical order. If we look at this, this is a resistor, which means the true label should be resistor. For me, that is 0, 1, 2, 3, 4. I'm going to change that to 4. And I have a note here to say that this is a resistor. And saved model should point to whatever got unzipped here. You probably don't need to change that. Note that if you go to model testing, click classify all if they have not been classified, and you can see what the model predicted for each of the test set samples. In fact, instead of using this known good resistor here that was part of the training set, let's use one of the test samples. And this is up to you on what you want to look at. You can look at validation, you can look at test, you can look at training. I'm going to take a peek at this resistor that the model thought was a capacitor. So I click on the little options menu here, say show classification, give it a moment, and it will pop up with the image and the output of the classification, which it was very sure that this was a capacitor. We don't want raw features, we want the processed features. So let's click those, and we're going to paste them into the image data here. Make sure we close off the list. Make sure we close off the list with a bracket. This is still a resistor. So 4 corresponds to the index of resistor here. We're going to run that cell. The next cell will load the model and give you some information about the model. So feel free to look at it here. It should match the model in your Edge Impulse project, which is noted here. Then we need to reshape the image, as what was given was just a list of features. Note that you will probably need to change the width and the height variables here to match whatever was set in the Impulse design page here. So 28 by 28 is your width and your height. You want to set them here, 28 by 28, and that's what determines how the image gets resized. So instead of being one long list, it's now a 28 by 28 array. We ran this. This is what our image looks like. The Keras model that we're going to be using in our algorithms expects a bunch of these together and color channels. So we need to actually put this in a 4-dimensional array, but if you notice, it's still just a 28 by 28 image that has a dimension of 1 for the color channels and then a dimension of 1 for the number of samples, since it's only one sample. That's all we're working with right now. We'll run that. We also want to do a forward pass of the model with this input image. That should give us the predictions, which should match our test sample. If we go here, we go to our resistor that looks like a capacitor. We show classification. And it should look something like this. TensorFlow takes a moment to start up the first time you run it, so be patient with it. And sure enough, we round that up to 1, and that looks about right. It really thinks that this is a capacitor. As I mentioned earlier in the slides, we need to remove that softmax activation function that's in the last layer of the densely connected neural network. That's part of our convolutional neural network. And to do that, we just call model, go to the very last layer, which is given by this -1 index, and we change the activation to none. That removes that softmax for us. First up, we're going to show the saliency map. This relies on the back-end TensorFlow library to compute gradients for us. And we're going to use the gradients of the loss with respect to the input image in order to generate that heat map. This becomes our function, which we can just call here, where we give it images, which is really just our one image, given here. Our model file, the only thing that's changed about that is changing the activation layer, and then the actual class of the image, which we got from the test set. This should be 4, which corresponds to resistor. That's used to compute the loss between the predicted value and the actual value during this gradient function up here. We'll run that. We then show the saliency map, which gives you an idea of where the network was looking at the individual pixel level on the input image. And then we can overlay that image with our original image. So we have this on top of the resistor, and you can see it's looking at the top edges here. It's not looking at the component body, In fact, it's completely ignoring the bottom side and ignoring the leads, it seems, except for maybe this area over here. And it's also looking a little bit at the background, which is interesting. My thought process here is that the network is actually looking for values to be not background somewhere in the center. Because this resistor is high up, it thinks this is a capacitor because that's where it's expecting the capacitor component body to be, since it takes up more space on this image. Once again, that's a hypothesis that I would need to test and maybe get additional training data in order to feed the network more images like this, where the resistor is not centered all of the time, to teach the network that, hey, a resistor can be up here. You need to look at other features in order to determine that this is a resistor and not a capacitor. Let's look at GradCam. Once again, we're using the back-end TensorFlow library to compute the gradients. This time, the gradient is the output neuron, or the output node, with respect to the output feature map of the last convolution layer, which is what we saw in the slides. We're looking at the feature map of that final convolution layer before it goes to that final max pooling layer and before it gets flattened to go to the densely connected neural network. We use that to produce our heat map. And in order to call this function, we need to tell it where that final convolution layer is. So what I'm going to do is print out all of the layers in my network, and I'm going to go backwards through them to find where the final convolution layer is. The name of that should be conv2d_1. It prints that out, and sure enough, that's the name of the final convolution layer. If you have 3 or 4, it should still point to that last convolution layer that's in the network. We then call the function with the name of our last convolution layer. That creates our heat map, and then we can draw that. As you can see, it's focusing once again on the resistor in the upper part of the image, and let's overlay that with our original image. This gives you a slightly different look at how the model is operating and where it's focusing its attention. With both the saliency and class activation maps, you can see that the model is focusing on the upper part where the component body is. However, you would want to compare this with something like a capacitor to see if the model is indeed focusing on that upper part for capacitors. This gives you some insights to how the model is working and can help you debug potential errors, especially for your test set images or your validation set images where the model failed to predict the correct class. In a future lecture, I'm going to go over data augmentation, where we can use this relatively small training, validation, and test sets to create or automatically generate new samples that can be fed into the model to hopefully correct some of these issues. Hopefully these heat maps generated by the saliency and GradCam functions can give you an idea of what you need to do during that data augmentation. So for example, if I wanted to be able to classify resistors in the upper part of the image, perhaps some of that augmentation would be, let's create more images out of the ones that already exist where the resistor is in the upper part or lower part. So we can start to move things around in data augmentation based on information we've learned from these mappings. One way to deal with an inaccurate model or one that's overfitting is to give it more training data. If you can't or don't want to collect more data manually, then you can use something known as data augmentation, where you automatically generate slightly modified versions of your original images to create a new data set. I'm going to show you some very simple image transformations you can do in order to augment your data, and this is running a collab that you can find in the course GitHub repository. To begin, make sure you've connected to the runtime, and then I'm going to upload a single sample, and I'm going to continue to use this first resistor sample that we collected. Once that's uploaded, what we can do is set the path to the image, so 0.bmp, and you're welcome to keep the seed as the same or change the seed. That's so you can get the same exact results that I get, assuming you're using the same input. And hopefully that works for most of the random calls that you'll find in this collab. So we'll run this. Then we're going to load our image as a NumPy array, which you saw way back when we were doing data collection. Now that our image is a collection of numbers in an array format, we can use that to get the height and the width of the image. Then we're going to view the image. I always like to do this just to make sure I know what kind of data I'm working with. As you can see, it's a 96 by 96, and there's 3 color channels. And I'm going to keep these images as color images. And then when we upload them again to Edge Impulse, I'll use Edge Impulse to convert it to a grayscale image. This is in case you want to work with this data set as color images instead of just grayscale. You can see that the individual color channels are still 8-bit values going from 0 to 255, and here is an output of that image. It should be exactly the same as our bitmap image. And you can double click these, and sometimes it'll show you an image preview over here, but it looks like in this case it doesn't work with bitmap, so it just tries to download it. One of the simplest transforms you can do is a simple flip. And here we're going to flip the image horizontally, we're going to flip the image vertically, and then we're going to flip the image horizontally and vertically. What this does is not only does it move your subject around a little bit, but it also accounts for any variations in light that the classifier might be picking up on. For example, resistors might be shinier than some of the other components, so that the neural network is looking for this little reflection in the resistor at this particular point in the image, or it's looking for a highlight or a shadow. And by flipping it, especially vertically, all those things are now in different spots. So it tells the classifier that, hey, you need to learn different things about this object than maybe where a reflection point is. Hopefully this will help kick it into gear in order to pick up on the shape of our subject rather than other features that we don't care about, like background or reflection points. Flipping horizontally can have this effect too, especially if it's looking for things like, oh, the gold band is always on the right because I forgot to flip the resistor when I was taking images myself, and instead it goes ahead and flips it so now the gold band is on the left, telling the classifier that it shouldn't always look for one of these bands and that it should try to pick up on something else. And same thing with some of the other color bands. I really should be using resistors with varying degree of color bands because there's a good chance that these color bands are being picked up by the classifier. But moving on from there, the next thing we can do is rotation. This takes the image and rotates it. Here I'm doing a 45, 90, and 135 degree rotation, but you can really work with anything. You could do, I don't know, 15 degrees, and that affects it in a different way. Note here that I'm using mode edge. This tells the transformation function, in this case rotate, whenever it rotates the image to fill in any blank spots with whatever pixel values it finds along the edge. So another way to look at this is if we change that to constant, it's going to fill it in with a constant value, in this case black or 0. And as you can see, the image is rotated, but these black bars may not be useful. In fact, they may be detrimental if you're not working with a dark background, like I am here where I've got this white background. It's going to tell the classifier to look at these dark backgrounds, or it might tell the classifier to look at these dark backgrounds. So if you've got a dark background, great. If you've got edges that can be extrapolated out and create something that looks like a decent image, then going with edge here is something that I completely recommend. As you can see, it tries to fill it in with either the background or the leads of this resistor, which is totally fine. I'm okay with it doing that. And then same thing here. The image actually ends about here, but it goes ahead and copies the pixel values from that edge outwards. And it ends up looking like leads on a resistor, which is exactly what I want. So this may or may not work for you, but it works great for these electronic components. Then we have scaling and randomly cropping. You might also see this referred to as random zooms. What we're going to do is actually increase the size of this picture. So instead of 96 by 96, it becomes 120 by 120 or 240 by 240, however big you want to make it. So this image is now bigger, and we're going to crop a section of that resized image to create something like a window that might look at this part of the resistor or this part. And it has the effect of moving your camera around or maybe a little closer to the resistor. In fact, you can see it even looks blurry here, which replicates the idea of moving my camera around so that the resistor is not always completely centered. This is a great way to make it look like the subject's not always in the center of your frame without having to take a bunch of extra pictures doing that. You can zoom out, there are transforms for that, but because you don't know what pixel values are outside the edges here, you're gonna have to guess. So you can either make them all one color, like black or a dark color, or you can use that edge extrapolation where it just kind of copies the pixels out. And for something like this, the leads look like they would just extend out, which is fine, and the resistor gets a little bit smaller. That's another way to do it, but this scaling and cropping works pretty well. Next, we have translation. This is where your object is just moved to a different part. We're not zooming in, we're not changing the size, it just moves it around. And this helps the classifier figure out the shape of the object rather than looking for it in a particular position. This is another great way to train a more robust classifier where your subjects are not necessarily dead center. And I actually do a random translation with this code where this resistor might be up here or it might be over here, up to about 1/4 of the way over. That way I'm not cropping too much of my subject out of the frame. And I'm actually doing this using the random.random function, not necessarily setting, I'm going to put the subject in this corner, this corner, this corner, this corner. That is another way to do it, but rather just kind of take a random smattering, because if you have more than one original images, you should end up with a good amount of random translations throughout your entire data set. Finally, the last one I want to talk about is adding noise. There are a number of different types of noise you will find in images. If you're working in darker environments, or if you've got your ISO or gain setting cranked very high on your camera, you're going to have something that looks like this center image, where it's very noisy. Noise is amplified in order to capture it, which is something that you'll run into often, especially with low light photography. But you can also run into it in any instances if you've got, say, a bad camera or a cheap camera. Introducing some noise is a fantastic way to emulate that, especially if you're trying to train a data set that was captured from a different camera that may not have that noise. This is part of the reason I always recommend capturing your training, validation, and test data sets from the same sensor that you're planning to use in deployment. This type of noise shown in the center here is known as Gaussian noise. It's what you'll commonly find added to images when you increase the gain. So this is a good one to use. Another type of noise you might come across is known as salt and pepper noise. This is evidenced by this image on the right here. Salt and pepper noise is different from Gaussian noise. It sometimes results from bad or poor analog to digital conversion when you're capturing an image. It shows up more often in black and white photos from what I've seen, but it's still something that you can have, and because it's different than Gaussian noise, it might be worthwhile adding into your training set just to give your model something else to look at where it tries to learn the shapes of things rather than trying to pick out individual pixel values, which who knows exactly what value they will be with a bunch of noise like this, and the noise will be different from image to image. Even with just the simple demo I showed you, that is 12 new images from just that one original image. If we include the original image, that means we can increase our data set by 13-fold. However, this is only a brief sampling of some possible augmentations. I didn't even include stacking the transformations, like flipping, cropping, and adding noise to create one image. You could exponentially increase the size of your data set if you start creating 4 rotated images for every flipped image. There is a whole field of study around data augmentation, and it gets into more advanced transforms that we didn't cover here, such as zooming along one dimension and playing with the color balance and contrast. I recommend starting with some simple transforms at first to see what works and what doesn't. This might mean training multiple models and comparing their validation or test results with one another. I uploaded my augmented data set to a new project in Edge Impulse. If we go into data acquisition, you can see that here I've got over 2,500 items in the training set and 655 items in the test set. And you can see the number of items in each of these. This is a lot more than my original set, which was just 50 of each class. Now I've got over 500 in each class, and most of that is being used to train my new classifier. If we take a look at the impulse, I'll first go into the feature extraction area. You can see that this is the augmented data. Here's one with noise, and I've converted them all to grayscale, 28 by 28 resolution, just like the original training that I did. So the model should be the same. It's expecting the exact same input data, and it's actually going to be the same architecture. I left it as the default Edge Impulse convolutional neural network with 2 convolutional layers, then a flattened dropout, and then our 5 nodes for the classifier. I trained this using 100 training cycles And you can see that it's actually a lot more accurate than before. And that's because I'm working with a lot more data and more variability in the data so that the model can learn the features that I'm trying to teach it, and not things like looking at the background or if there's just two leads, things that were in the original photos but might not be fully represented in different camera angles, lighting conditions, or even if you're moving the object around in the frame. As you can see here, the model still struggles a little bit with the diode and the resistor and the LED and the capacitor, but it's a lot better than what it used to be. If I go to model testing, I've classified all of my test data, and you can see there are some misses here and there, but it's still maintaining about 97% accuracy, which gives me much more confidence that this model is going to work better when I go to deploy it. Something else you can do is look back at our saliency and class activation maps to see what the model's looking at this time. It struggled with capacitors and LEDs before, or trying to determine the difference between resistors and diodes. It looked like it was trying to examine the backgrounds for some LEDs. In fact, let's take a look at this LED that was misclassified, and we can probably determine what was going on. First of all, you see that it got shifted, so it's missing this round cap, which makes me believe that this image might be shifted a little too much during data augmentation, which is okay. I'm happy to have some things that aren't classified properly because it helps us figure out what the model is looking at. I'm going to copy these features, and we know that this is an LED. I'm going to go into my Colab script here and start running it. The other thing I need to do is download my saved model, which I'll do here. I'm going to upload the model. And since I've already downloaded this before, I need to rename it because these parentheses do not work well in Colab from what I've determined. So there's the name of my model. I'm going to copy the path, paste it here. That should unzip the model for me. And then I need to get the processed features because I accidentally removed everything on my clipboard. I'm going to put them here. And this was an LED, 0, 1, 2, 3. LED is correct. And I'm going to run through these so we can take a look at what the saliency map looks like as well as the class activation map. If we look at the saliency map, we can see that it's focusing on the pixels in this bottom part here, which might be LED, might be resistor. We're not quite sure, but it is missing this round part of the LED. Interestingly enough, the classifier is looking in the center here, and I can see why it might think that's a resistor because it kind of creates this oblong shape right in the center, and it's missing that cap or any other edges. So that would make sense why this got misclassified. That being said, it's a lot better than trying to look up top and down below for the background, which it still might do, but this is a good start and you get an idea of what's going on with the model. Data augmentation does not always work, but it can be useful if your images are fairly similar, and especially if you're working in a controlled environment where the background doesn't change much, like what we've got here with the different components on the white background. Your best bet is to always collect more data that represents your target use case, but failing that, data augmentation can be quite powerful to help you train more robust models. Training complex machine learning models, there is a slick trick we can use called transfer learning. With this, we reuse a part of a model that's been previously trained on a different but similar data set. Let's look at our very simple convolutional neural network as an example. Let's say we fully train this model to identify electronic components. The feature extraction portion of this model, which consists of all the convolution and pooling layers, has been trained to recognize certain shapes and patterns that make up those electronic components. This includes basic shapes that are large in the frame based on the training data. Now, let's say we wanted to train this same model to recognize something else, like nuts, bolts, and screws. We could retrain all of the filters and weights. For a small model like this, retraining everything would not take a long time. However, when we start to look at much larger and more complex models, fully training all of the weights might take hours or even days. So it makes sense to reuse parts of the model where we can. To reuse a model, known as transfer learning, we would freeze whichever layers we want to keep. For things like image classification, we often want to freeze the convolution and pooling layers, as we assume that they have been trained well enough on images that are somewhat close in structure to our new dataset. Freezing means that when we run the training process next time, the parameters in the frozen layers are not allowed to change. Next, we remove the layers that were not frozen and replace them with whatever we want. This might be a totally new flattened layer with different fully connected nodes. You could even add more than one fully connected layer or other layers if you desire. Note that our outputs change too, as we might want to recognize a different number of classes. We then run the training process again on this model using our new dataset, which consists of nuts, bolts, and screws. This time, the convolution and pooling layer parameters are not updated. Only the new layers are updated. We are essentially saying that we're happy with the features that the first part of the model has extracted for a given problem, and we're going to use that for our new, but similar problem. The dense neural network classifier is the only thing that gets updated at this point. When training is done, you might see a second training process occur called fine-tuning. Here, we first unfreeze any layers. We then run the training process again with a very low training rate, which means parameters are not allowed to change very much. This causes all the parameters to adjust slightly as necessary to pick up any minor variations in the features from the original training set. At this point, we hope that the model is capable of correctly identifying screws, nuts, and bolts instead of electronic components, and we'd want to test its accuracy on a validation or test set. Note that we have to use a dataset that has similar features to our original dataset. I would not expect this model to work well identifying cats versus dogs, as the feature extraction portion has been trained to look for very simple shapes in electronic components rather than complex features like eyes, ears, nose, and so on. There are two main reasons why you'd want to do transfer learning. The first is that it saves you a lot of time. Some of the more complex models out there can take hours or days to train from scratch. Using transfer learning can get this time down to a few minutes. Next is that we can work with smaller training data sets. Because we assume that the feature extraction portion of the model has been trained on a similar data set that's close enough to our problem, we only need to train the classifier portion. As a result, we can often get away with a few dozen training samples rather than a few thousand per class. Before we move on to discussing MobileNet, I'd like to make a quick note about model diagrams. I will try to draw my model layers going from top to bottom, with the input at the top and the outputs at the bottom. This is to mimic how you might see the model described in Keras or in the Netron app. However, in many machine learning articles and papers, you might come across the reverse, with the input at the bottom and the output at the top. An article might refer to replacing the top layers during transfer learning, for example. In this case, they're referring to the dense layers that make up the classifier portion of the network, which happen to appear at the top of this particular diagram. You'd have to look at any provided diagrams or infer from context whether the author is thinking about the network model being top to bottom or bottom to top. You might also see left to right sometimes, which just adds to the confusion. The models all work the same mathematically though. I generally try to stick to top to bottom for any content that I create. Over the years, researchers have put together collections of pre-made data sets for people to use with machine learning. These are popular with competitions or for using as the basis for purpose-built models. Classifying images is such a big problem in the machine learning world that there are many such data sets for images. One of the most popular data sets is CFAR, and there are two versions, one with 10 classes of objects and another with 100 classes of objects. The images are all the same size and have all been labeled, which makes it perfect for training a model. Another large collection is the ImageNet dataset, which contains over 14 million images, and these images have all been labeled with one of 1,000 classes. An interesting feature of ImageNet is that the labels are part of a hierarchy. This can help you train a model that recognizes just a dog as a label or a specific breed of dog. COCO, which stands for Common Objects in Context, is another image data set with over 300,000 images and 1.5 million objects that have been labeled in those images. Which pixels make up the objects are also noted in the ground truth information. This is useful for training a segmentation model. We'll talk about object detection and image segmentation in the next module. Along with collections of data sets, researchers in industry and academia have created families of machine learning models designed to tackle specific problems. As image classification is one particular problem that's in very high demand, there are a number of models that have been developed specifically for image classification. Because ImageNet has such a large number of classes and a huge number of samples, it provides a great benchmark to test the accuracy and efficiency of these models. This particular paper compares the accuracy and computational requirements for many of the top neural networks. ResNet and VGG are two very popular models. You can see that they have decent accuracy. Some of the more accurate models also require many more operations. Since we are working with embedded systems with limited resources, we want to use a model that is closer to the left side of the graph, as these should be less computationally expensive. We will be looking at MobileNet v2 as it was specifically developed for embedded and smartphone applications. While it might not be the most accurate model for image classification out there, it is very efficient while still performing decently well on such classification tasks. Here is what a version of MobileNet v2 trained on the ImageNet dataset looks like. As you can see, it's quite a bit more complicated than the basic convolutional neural network we were looking at earlier. It's designed to work with larger images, color as well as grayscale, with many more complex features and many more classes. There are some layers in here that we did not specifically cover, but this is still essentially a collection of convolution and pooling operations. This depth-wise convolution operation performs convolution on the 32-dimensional feature maps that come from the previous convolution operation, but then it leaves the third dimension alone, creating a new stack of 32 convolved feature maps. The output from some of the layers are added to the output of future layers in what's known as a residual block. These skips resemble how the pyramidal cells in our brains work. They also help fight a problem in training known as vanishing gradient, where the parameters stop updating due to a very small gradient being calculated during backpropagation. MobileNet v2 also contains a number of bottlenecks, where the number of neurons or convolution filters in a layer is fewer than the layer above it. For example, the output of one layer might be fewer two-dimensional feature maps than the layer before it. Then you'll see the number of maps get larger again. These advanced techniques help the model learn complex features of images. At the end of the feature extraction section, you'll see that we're left with a bunch of 7x7 feature maps. A global average pooling operation is applied to each of these feature maps to create our flattened array, where each element is an average of the feature map values. From here, we can perform our classification using a densely connected neural network to make a prediction of the label of the input image. When working with transfer learning, we often want to start with a pre-trained network like this one. All of the weights for the convolution filters have already been set by training this model on a known good dataset like ImageNet. Here is a version of MobileNet v2 that I used for transfer learning in Edge Impulse. What's interesting is that we can change the input to MobileNet somewhat. Instead of a 224 by 224 color image as input, I modified this one to accept 48 by 48 grayscale images. The convolution layers still work the same, as they're not really dependent on having a particular size and shape for their input. The only thing we have to be concerned with is that at the end of the feature extraction chain, after the convolution layers reduce the dimensions of the feature maps, individual output feature maps are not smaller than 1 by 1 pixels. This means that for most applications of MobileNet v2, the smallest input shape is 32 by 32 pixels from a grayscale image. Edge Impulse removed the average pooling layer for this particular model and added 2 fully connected or dense layers for classification. This is the section that gets trained during transfer learning. However, all of the parameters get tweaked a little bit during the fine-tuning stage. I used this model to identify when my dog was present in the frame or if it was just an image of my empty office. That's why there's only 2 outputs. However, you can use MobileNet and transfer learning to create a model that can predict any number of classes, of course within reason and the capabilities of MobileNet and your processor. Keras, as well as Edge Impulse, comes with a collection of pre-trained MobileNet v1 and v2 models. Note that common pre-trained MobileNet v2 models were trained on ImageNet or Cocoa images with specific resolutions, like 96 by 96 or 224 by 224 pixels. That means if you don't use one of those resolutions for your input, you might lose some accuracy, as that's what the parameters were trained on. Something else that you can adjust is this alpha hyperparameter. This controls the number of filters in each layer. A larger alpha value means more computations and a more complex model. This could mean more accuracy, or it might mean more overfitting, so you should try a few values of alpha to see what works best, or start off with the lowest alpha to see if that works well enough for your problem. Here is the original paper that proposed MobileNet v2. In it, you can find a chart that gives you an idea of its accuracy on the ImageNet dataset compared to other models. As you can see, version 2 generally works better than version 1. You can increase the resolution of the input image, which can help with accuracy. However, it often means more computations are required. Once again, for embedded work, you'll want to find the most efficient model capable of performing your task with your desired accuracy. Transfer learning, which reuses parts of a previously trained neural network, is an incredibly powerful technique. It allows us to quickly create models that meet our needs and with less training data. Now that we've seen how transfer learning works in theory, let's put it into practice using Edge Impulse. We'll be using MobileNet v2 that's been pre-trained on the Cocoa image dataset and then tweak it for our project. To start, you'll want to collect a new dataset. You're welcome to use the old dataset that we were using in the first part of the course, but I recommend trying something new here. One of the advantages of transfer learning with a complicated model like MobileNet is that we can do things like have complex backgrounds and have our shape or object or objects that we want to detect within those complex backgrounds. And by that I mean a variety of background shots. Here is a bunch of shots from my office, just at different angles, different positions, places where I would predict I might find my dog. And you should do something similar. I'm going to be creating a dog detector. Specifically, whenever my dog is spotted in the frame, I'm going to get notified from my OpenMV, my Arduino, whatever it is, my embedded system that I'm training this model for. And I have a bunch of different photos of my office from a various number of angles, zoom levels, and whatnot. It's all around this backpack, as you can see, because that's where I'm going to hopefully see my dog, and it's kind of gray. I also got a number of photos of my dog in various positions, and I'm using the OpenMV to capture these, but feel free to use whichever device you'd like. These are all done with a 96 by 96 resolution and color, but we're going to ultimately convert these to probably something like 48 by 48 and grayscale. And as you can see, I just have my dog in a variety of positions here. Hopefully I can create something that spots the dog, and you need about 50 samples per class. And I only have 2 classes here, background and dog, but you're welcome to do a multi-class classifier. I know that in the Edge Impulse documentation, they show you how to do something similar that is background, plant, and lamp, and you can identify one of those 3. So it can be binary, it can be multi-class. Just make sure you have about 50 samples of each, and as you can see, I don't need a perfectly white background as we're using a fairly complex model here. Once I'm done with that, you'll notice that these are in bitmap format. To work with Edge Impulse, whatever format you were using, I recommend converting them to PNG, and I've got them here. They're all nicely labeled. Here's the ones with my dog, once again 96 by 96 resolution, and here are the ones with the background in just a variety of positions here. As you can see, I got a few more here than just my backpack. It's all around my office. And from here, we can go to Edge Impulse. Once in Edge Impulse, sign into your account and create a new project just like we've done before. I'm going to call mine Dog Detector. Once at your dashboard, click out of the pop-up. We don't need anything from here. We can go right to data acquisition. and upload your samples that you collected. Remember that you need PNG files. I'm going to go to wherever I keep my data set, PNG version of my dog detection data set. I'm going to start with background. I'm going to select all of them, click open. I'll let it automatically split between training and testing, and I'm going to enter the label of background. I'm going to do the same thing again for my next class, which is dog. Change the label to dog and upload again. And you'll want to do this for all of the classes that you have, and it could be 2, it could be 1, whatever it is. Once it's done, I recommend clicking on data acquisition and making sure you have your 2 classes with 50 items between the training data and the test data. Once you're happy with that, go to Impulse Design. You can stick with 96 by 96, but I found that for some of the lower end embedded systems, 96 by 96 is a little big. So this didn't even work well with my OpenMV H7, the non-plus version, but it would probably work with the plus version. So to make things work, I recommend going 48 by 48. And remember, 96 by 96 is a common format that MobileNet was trained for, so I might lose a little bit of accuracy by downscaling or resizing the image to something that's smaller, but hopefully it will still work for our purposes. Just, I recommend working with something that is the lowest resolution possible that gives you the accuracy that is good enough for what you need, because then it means you can work with lower resources on your embedded system. Next, we're going to add a processing block. We're going to stick with image, and then we're going to add a learning block. Instead of using a regular neural network this time, we're going to use transfer learning, and this allows us to use or start with a pre-trained network. Click Save Impulse, and then go to Image, where we're going to do more or less feature extraction for our images. In this case, we're going to start with the color images. We're going to go to grayscale, and they're going to be converted to 48 by 48. They're going to be resized from 96 by 96 to 48 by 48, and that will be the input images for our training. So click Save Parameters, and then click Generate Features. Once that's done, you should see the Feature Explorer appear, and you can take a look at where your classes are. Remember that this is just a very simplified visualization of your images because there are more than 3 dimensions in your image. There are hundreds or thousands of dimensions, and these just get reduced to something that you can kind of get an idea of certain aspects of the image. And it looks like it's going to be fairly separable here, which means that we should be able to train a decent model. Also, don't forget, because we're working with 48 by 48 images, you will need to supply the model a 48 by 48 grayscale image during inference, whenever you go to deploy that to your embedded system. Let's go to transfer learning. I'm going to bump this up to 50 cycles. I find that 20 is a little low sometimes because I like to just train things for longer and see what we get. The learning rate is fine. I'm going to choose to not do basic data augmentation at this time. And it looks like it starts us with MobileNet v2 0.35, and 0.35 here is that alpha parameter, which just determines the number of parameters or the number of filters in that feature extraction portion of MobileNet, which means that we can potentially get a better model that can identify more complex features with more of those filters, but it means more resources and we run the risk of overfitting. You can click on the first button to edit the number of neurons in that final dense layer to help with your classifier once it's done with the feature extraction that gets added on and trained separately as part of the transfer learning process. There's also a dropout layer that you can affect. 0.1 seems to be fine, or you could delete the whole model. I'm going to choose to use a different model here. In fact, I'm going to look for MobileNet v2, which generally works better than MobileNet v1, and I'm going to pick one, honestly, with the lowest alpha rate here, simply because I'm working with such a simple data set and I want to use as few resources as possible for RAM and ROM, which are shown here for each of the potential models. As you can see, as you start going up in image resolution, this is the resolution that the input expects, but it can be changed. The minimum is 32 by 32 pixels. We're going to use 48 by 48 because the parameters that resulted from training this model on ImageNet were set for this resolution, so expect a slight drop in accuracy. As you go up in the resolution as well as the alpha, you're going to start using more resources. In fact, here's one that uses over a megabyte of RAM, so keep that in mind when choosing a model and what kind of embedded system you're working with. Even the smallest model that we have uses a good amount of RAM and flash memory, so pay attention because MobileNet still requires a fairly beefy processor with lots of resources and usually a fast clock speed in order to work. So I'm going to choose this one with 0.05 alpha. I'm going to click Add, that appears here, and I'm going to click Start Training. This is going to show the training output on the top right, and we just wait for a while until this is done. You'll see that it queues up on their server, and it's going to train the model. Whenever it says training model, that means it's training the classifier portion that's after the feature extraction that we saw when we were looking at MobileNet v2. So those parameters are going to stay the same because they were trained on ImageNet, which is that large database of images, and we're just training that classifier portion to work with our project here, dog versus background. Next, it's going to fine-tune, which means that it unlocks or unfreezes all of the parameters, sets a very low learning rate, and just tweaks them a little bit. It's not going to take very many epochs in order to do this. When it's done, you should take a look at the accuracy and validation accuracy. Hopefully these are over something like 90%, which is really, really good for something like this. And as you can see, this trained very quickly in comparison to our fully training model, even though this is a much more complicated neural network. When it's done, it's going to show you the validation set performance. 88.9% is not bad. It looks like it struggles some with a few background and dog images on the validation set. You can see those in red dots here where it misclassified those. But this is not a bad starting spot. In fact, I would be happy to deploy this knowing that some frames may be misclassified, and I can go back and look to see which images might do that. In order to do that, we can go to testing and use the model to perform inference with our test set that we set aside at the beginning. Let's classify all of those and see what happens. When it's done, you can see that we have an accuracy of 92.3, and the only thing that it missed is that one of the dog images, it considered it to be uncertain. It didn't even misclassify it just didn't meet the threshold. So we can look at that to see where it was misclassified or try to figure out what was going on here. When you load it, it looks like my dog was looking away. There's no identifying features of eyes or mouth that are clearly in the frame. So I can see why this might have struggled. In fact, it still thought it was a dog, but it just didn't meet that threshold and it counted it as uncertain. I believe it needs to have a 0.6 threshold in order to count it as I know that this is a dog. So it struggled a bit. This makes total sense. So I believe the model needs to have the dog looking at the camera, or at least a solid profile picture of the eyes, ears, snout, in order for the feature extraction portion to pick up on those features, because that's what it was trained for when it was trained with ImageNet. And I'm okay with this being misclassified for my particular deployment. The other thing you can do is try playing with some of the hyperparameters that you can find in the learning section. So some of the options here where you can pick the number of neurons and you can adjust the dropout rate, that may help, or you might have to try a different model, maybe a different resolution for your particular project to get an accuracy that you are happy with. When you are done, head to deployment, and you have a number of options to work with. You can do a strict C++ library to work on any number of systems, assuming you have some way to compile C++ files. The other thing you can try is an Arduino library. There are a few Arduino boards powerful enough to support MobileNet. The Portenta is one of those, but if you're working with the Portenta or the OpenMV camera, I recommend using the OpenMV because it's much easier to work in MicroPython. But if you need C++, you want that absolute efficiency and execution speed, then try the Arduino or the C++ library. Finally, there's also a way to deploy it to Linux boards if you want to get this working on a single board computer. Once you've selected the library or output that you'd like, click Build. It's going to create the library, and it will download it for you. From there, you can deploy it to your system of choice and give it a shot. I copied the trained.tf lite and labels.txt file to the SD card of my OpenMV camera so that those would load into this program. I also changed the frame from 96 by 96 to 48 by 48 because I have no good way to easily resize images captured in the frame over here, and that's just something that is with OpenMV. There are Python libraries, or you can write your own way to resize images as you capture them, but capturing a pure 48 by 48 image seems to work well enough. I'm also capturing in grayscale this time so that the image is ready to be fed directly to my model. Much of this should look very similar to the original densely connected neural network that we did earlier if you were using the OpenMV-CAM. Once we have the image, we can feed it and the model file to this tf.classify function that classifies the image for us and gives us the prediction back as a collection of objects. We look at the first one since we're only doing a single classification. We're not trying to do several classifications or object detection yet. With those predictions, we can print out the probabilities in our serial terminal. I'm only doing that once every few inferences, so you're missing a few when things are being printed to the console, and that's okay. However, I am drawing the label and the probability of that label to the background image in OpenMV so we can take a look at what's going on. When I point this around the room, you can kind of see that it works pretty well. It's looking at my crazy rug here. There is dog, and it identifies my dog as dog. And it looks like it identifies dog even without the face, but it struggles a little bit. My guess is if it has a face, if it has the face in the frame, it definitely knows that it's my dog. However, if it's just the body or part of the coat, then it struggles a bit, probably because it's looking at various patterns like the black stripes on the light background. If I move around my office some more, you can see some boxes and back to dog. And if we come back to this area where there are some cables hanging down, you can see it actually misclassifies those as dog, which is part of what makes me believe that it can identify the backside of my dog. Because those stripes on the back are dark against a lighter background, I did not have these cables hanging down as part of the training set, so it doesn't know that these should not be classified as dogs. That's something I can learn by testing in a live environment. I should capture these, put those in my training set so that it does not misclassify them as my dog. But I could set up my dog recognition machine here to automatically open a door or give Pippin here some water or food or whatnot. Pippin. Pippin. Who's my good boy? That is dog. So in addition to dog, you can also make a person classification machine to identify if people are at your door, say if they're ringing your doorbell or about to, maybe set up something to prevent somebody stealing a package, or if somebody's in your home and you need to know, or you want to turn on lights or turn on a fan or the air conditioner. This is another way to do a detection to see if somebody is in an area. I hope this helps you see how you can use transfer learning to train a model that's been trained on other objects in order to very quickly produce something for an embedded system. I know that we covered a lot in this module. Let's take a moment to review what we've learned. First, we talked about how image convolution works. This is accomplished by sliding a window across the image with a given stride and performing an element-wise weighted sum of all the values underneath the window. This produces a single output in a new array that constitutes a feature map. Here is the general form of convolution, assuming we're using a stride of 1. Without any sort of padding of the input array and using a kernel larger than 1 by 1, we'll end up with an output array that's smaller than the input array. We could also pad the input array or image with zeros or copy the values at the edges to make the input bigger. Usually, we would want to add enough padding so that the output array is the same size as the input array. This is known as same padding. No padding is known as valid padding. Convolution is an incredibly important method that allows us to filter an image in a variety of manners as shown. We can blur, sharpen, or create interesting effects like this embossed image. We can also use convolution to detect edges in the image, which forms the basis for how many computer vision techniques detect objects, including convolutional neural networks. Another important function you will see is pooling, and there are two common types, average and max. In average pooling, a window slides over the whole image, and the pixel values under that window are averaged together. This helps to reduce the dimensions of an image or feature map. The stride in a pooling operation is almost always the same as the width and height of the window. In this example, the window is 2 by 2 and the stride is also 2. Max pooling is similar, but instead of averaging the values under the window, the maximum value is chosen instead. This helps to reduce the dimensions of an image while highlighting the most salient features. While both pooling methods have their uses, max pooling is more common after convolution as it helps to pick out the most important features. We then saw how these operations fit together to create a convolutional neural network. A series of convolution and pooling operations can be stacked together to create a feature extraction section. The weights in the convolution filters become the parameters in this stage, which get automatically updated during training. This helps the model learn the most important features in images in the training set, which are fed to the classifier section. Note that each convolution layer may have more than one filter. For example, if that first two-dimensional convolution layer has 16 filters, then 16 feature maps will be generated that are passed on to the next max pooling layer. Once the image has been filtered and pooled one or more times, the feature maps are rolled out or flattened to create a one-dimensional array or vector that is sent to a simple, fully connected or dense neural network. This network acts as the classifier in order to predict the label of the input feature set. When trained, this model will ideally figure out which features are the most important in any given image and use those features as calculated by convolution and pooling to classify the original input image. Next, we saw how we could modify a trained convolutional neural network to produce a series of visualizations to help us see what's going on. In both cases, we need to remove the softmax activation of the last layer as the math requires the raw output of the neural network. We first looked at saliency maps. In these, the pixels that are determined to have the biggest effect on the decision-making process are highlighted. The second was a gradient-weighted class activation map, where the features from the final convolution step are shown and the elements that had the biggest effect on the decision-making process in the neural network are highlighted. We can use the information in these maps to help us figure out how a convolutional neural network is making decisions. Specifically, it tells us where the network was looking in each input image or feature map to make its decision. Knowing that the model is looking at a particular area is a great way to identify potential biases or problem areas worth exploring. One way to fight model biases is to use data augmentation. Here, we can perform a number of image transforms on a single training image to produce dozens or hundreds of copies of that one image. For example, with 12 simple transformations, we can multiply our training set by 13, going from 250 images to 3,250 images. If a model was looking at a certain area of the image for a particular background or glint of light, this process can help tremendously by moving or flipping the object in question. In other words, it keeps the model on its toes when training. Finally, we looked at transfer learning, where we can take a pre-trained model, freeze some of the parameters, and train a new classifier. This can help us reuse a model that's been trained on a similar set of data. For example, we looked at MobileNet v2 that was trained on the popular ImageNet dataset that contains millions of images categorized into 1,000 classes. We freeze the feature extraction set of parameters, remove the classifier section, and add our own that corresponds to the specific problem we want to solve, such as making a dog or person detector. We then train using the whole model, but only allowing the parameters in the final few layers to update. A final fine-tuning step can be performed where we unfreeze all of the layers and run a few training epochs to allow all of the parameters to update a tiny amount. This allows any parameters to shift a small amount as needed to better work with our data. Transfer learning allows us to train complicated models much more quickly, assuming we are working in a similar problem space. For example, using a model pre-trained on ImageNet to identify common objects like people, cars, animals, and so on. You would not want to perform transfer learning on such a model to identify things like frequency spectrograms, as the images are vastly different in their composition than the original training set. Additionally, since most of the parameters are already set, you can get away with far fewer training epochs. Training MobileNet from scratch might take 10,000 epochs or more, but you can do transfer learning in just a few dozen epochs. Transfer learning can save you a lot of time and energy. Now that we've seen how to classify images using both simple and complex neural networks, we're going to look at object detection in the next module. That's where we start to be able to locate an object in an image.